Okay, thanks a lot everybody for listening. My name is Hoerger. I'm a PhD student at the University of Queensland under the supervision of Hannah Kunyawati. And as we've seen already, every autonomous robot is inherently subject to uncertainties that typically stem from control and observation errors and limited information regarding the environments the robot operates in. Now the question is, how do we allow autonomous robots to make effective decisions under uncertainty? And a principled way to solve this is the partially observable Markov decision process, where the main components of the POMDP are state, action, and observation spaces of the robot. Furthermore, we have a transition function and an observation function that model the uncertainty in the effect of performing an action and receiving observations as conditional probability functions. And furthermore, we have a reward function, which is our objective function that we are trying to maximize. Now, due to the uncertainties the robot is subject to, it never knows the exact state it's in. Hence, instead of planning with respect to single states only, we plan with respect to probability distributions over the state space called beliefs. And the goal here is to compute an optimal policy, which is a mapping from beliefs to actions that maximizes the expected discounted reward the robot will receive when following this policy. Unfortunately, it has been shown that calculating the optimal policy is computationally intractable in general, but nowadays we have approximate optimal POMDP solvers that are tractable for realistic motion planning tasks. And these solvers can be divided into two classes. We have the general POMDP solvers, where in this context, general means that they do not impose any restrictions on the type of beliefs or the type of systems we are planning for. And the second class are linearization-based solvers, which restrict the beliefs to be Gaussian and the system and observation dynamics to be linear. Now, by imposing those restrictions, this class of solvers can significantly reduce the problem complexity and are therefore potentially able to find a good policy faster. However, it has been shown that linearization only works well for systems with mild nonlinearities. And furthermore, it is not clear what effects cluttered environments have on the quality of the policy computed by these solvers. So the questions we want to answer here is, what does it mean when we talk about mild nonlinearities in motion planning under uncertainty? Can we actually measure it? And furthermore, does this allow us to make a statement on the quality of the policy computed by these linearization-based solvers? And if we look at existing measures of nonlinearity, we see that most of these measures have been defined for deterministic systems only. And it is only recently that measures for stochastic systems have been proposed that in principle can be applied to our problem, such as that measure of non-Gaussianity here. However, these measures are not designed to take the effect of obstacles into account. And furthermore, the relation between these measures and the quality of a computed policy by a linearization-based solver is not clear. And this is exactly what we are trying to alleviate here in this work. So instead of building upon existing measures for stochastic systems, we extend recent results in the sensitivity analysis for MDPs to develop a new measure for POMDPs, which we call statistical distance-based nonlinearity measure. Now, this measure is defined as follows. Given a POMDP and a linearized version head, this measure consists of the summation of two components, where these components are defined as the total variation distance between the original and the linearized transition function and the original and linearized observation function. Now, the nice property about this measure is that the difference between the optimal policy for the original model and the linearized model is upper bounded by a function linear in S&M, where this here is just a constant term given a particular POMDP problem. Now, note that here we're using S&M as a global measure. However, we can also use it as a local measure around the current belief by computing it with respect to the support set of the belief and with respect to the set of observations that can be perceived from this support set. So in other words, by calculating a local approximation of S&M around the current belief, we can use the previously derived upper bound as a sufficient condition to decide when a linearization-based solver can be used and when it should be avoided. Now, based on this, we developed a simple threshold-based online planner which utilizes two component planners. First one is ABT, which is a general POMDP solver, and MHFR, which is a linearization-based solver. Now, at every step, we calculate a local approximation of S&M around the current belief. And if this approximation, using a Monte Carlo-based approach, and if this approximation yields a value higher than a user-defined threshold, we use ABT to calculate the next action, whereas we use MHFR if it's below the threshold. So now we want to evaluate both S&M as well as our planner, where we compare S&M with a state-of-the-art measure of non-linearity, the previously seen measure of non-Gaussianity. And to do this, we apply ABT and MHFR on two robotic systems, where we increase both the uncertainties the robots are subject to, as well as the clutterness of the environment. And the first robot is a car-like robot with second-order dynamics operating inside a 2D environment, where the state here is defined as the position, orientation, and velocity of the robot, and where these two beacons here are used by the robot to localize itself. Now, the second robot we are looking at is a 4-degree of freedom manipulator operating inside a 3D environment, where here the state is 8-dimensional and consists of the joint angles and the joint velocities of the robot. Now, for both robots, we assume that the controls and observation are disturbed by zero-mean Gaussian noise. Note, however, even though we assume Gaussian errors due to the nonlinearities of the systems, the beliefs will not be Gaussian in general. So for the car-like robot, we are using two problem scenarios, an empty environment and an environment with obstacles, where for both scenarios, we assume that the robot starts from a known initial state and has to reach a goal area, which are those green spheres in the upper right corner. Furthermore, the reward function is defined such that the robot receives a high reward when reaching the goal area, a large penalty when it collides with an obstacle, and a small penalty for every step it takes in order to promote shorter trajectories. Now here for the simulation runs, we first ran a set of preliminary tests to figure out the best parameters for every algorithm, and then during the comparison, we used the same planning time per step for both algorithms. Now, this graph here shows the relative value difference between ABT and MHFR as we increase the errors in both scenarios, where negative values mean that MHFR performed better than ABT, and vice versa for positive values. And as we can see in the empty environment, both solvers perform relatively similar, whereas in the cluttered environment, for small errors, MHFR actually outperforms the general solver ABT. But as we increase the errors, there's a significant advantage for ABT. Now, if we look at the comparison between S&M and the measure of non-Gaussianity, we can see in the first graph that in the empty environment, both measures increase correctly as we increase the errors, whereas in the second graph shows that in the environment with obstacles, the measure of non-Gaussianity actually starts to flatten out, whereas S&M keeps on increasing as we increase the errors. So now let's have a look at the more interesting problem, the 4-degree of freedom manipulator. Similar to the car-like robot, we're having two problem scenarios, an empty environment and an environment with obstacles. And here we can see that ABT significantly outperforms MHFR in the environment with obstacles, even for small errors, which indicate that in this problem scenario, the obstacles have a major effect on the performance of the linearization-based solver. Now, if we look at the results of the measures, we can see that S&M significantly increases in the environment with obstacles compared to the empty environment, which indicates that S&M can reflect the effects the obstacles have better than the measure of non-Gaussianity, which remains relatively the same. So after seeing those results, we are now interested in how does our S&M planner perform compared to ABT and MHFR. And to do this, we are using three problem scenarios, where the first two scenarios are similar to the car-like robot and the 4-degree of freedom manipulator scenario we used in our previous comparison. And additionally, we have a 6 degree of freedom manipulator operating inside an environment with obstacles, where here we have a 12-dimensional state space. Now this table here shows the expected discounted reward for all planners in all 3 problem scenarios. And as we can see for the car-like robot and the 4 degree of freedom manipulator, our planner actually outperforms the 2 component planners. Whereas for the 6 degree of freedom manipulator, our planner achieves similar results to the best of the component planners, which is ABT in this case. Now this indicates that S&M can indeed be used to identify when a linearization-based solver can be used and when we should use a general solver. So to summarize, we have presented a new general measure of nonlinearity for stochastic motion planning that can be used to identify the effectiveness of linearization-based solvers in environments with obstacles. And this allowed us to develop a simple threshold-based POMDP planner that switches between a general solver and a linearization-based solver with pretty encouraging results. However, there are also a few limitations regarding our presented method. First of all, computing S&M essentially means solving a stochastic optimization problem, which can be pretty expensive to compute. Furthermore, the derived upper bound on the value difference is relatively loose and can only be used as a sufficient condition to decide when a linearization-based solver can be used. And furthermore, we believe that we can significantly improve the relatively simple threshold-based planner by developing a more integrated planning approach that includes our measure. And that already concludes my talk, and then I'm open for your questions. Thank you.
Hoerger?
Yeah. So my question. So in this is in some way pretty abstract, right? Like linear. So I did not quite understand in what context linearization does have an advantage or disadvantage. So what does it mean for a transition function to be linear? What does that mean?
So essentially, by using linearization and that Gaussian assumption, right? So these solvers, they can reduce the problem complexity in a way that propagating a Gaussian distribution is simply propagating the mean and the covariance of the Gaussian. However, in the presence of obstacles, that Gaussian assumption doesn't necessarily hold anymore, right? So now we want to find out, okay, how strong is that assumption violated? And in order to answer this, we developed S&M.
Yeah, so what was not exactly clear to me is what kind of POMDP solver are you what is the representation of the belief in these solvers? In one case is it a Gaussian and in another case some set of samples or so?
Yeah, so specifically in our S&M planner, what we do here is we represent the belief by a set of particles, right? Now, and essentially, in order to approximate our measure, we have to, what we do is we essentially approximate the belief by a Gaussian distribution and then propagate it using the linearized model.
Okay, and so what is the choice here? This choice is made online, and in what case?
Yes, so this choice is made online. So I forgot to mention it before. So S&M planner is an online planner. And for the experimental results, we use 20% of the planning time to evaluate this measure around the current belief, where the rest of the planning time is used for these 2 component planners to calculate the policy.
So during solving one plan, you will switch online between different solvers?
So essentially, depending on the outcome of the approximation of S&M, we use a general solver or a linearization-based solver. So a priori, before we use those component planners to calculate a policy, we first evaluate the measure and then look at the result.
Okay, I'm going to let Ken get a word in because he has his hand up.
A very interesting idea. So I'm curious, why not just run them both in parallel rather than doing the overhead of computing the S&M?
Well, because essentially what we want to utilize here, we want to determine which solver will likely yield a good policy given limited computational time, right? So Yes, we could run them in parallel, but we are not trying to promote parallelism here. We try to estimate in advance which solver will yield a good policy given a limited computation time. But yes, indeed, theoretically you could also evaluate them in parallel and then see which solver, and then basically choose the policy depending on the outcome of your calculation. Yeah, that's true. But this is nothing that we are trying to look at here.
Okay, then just quick follow-up on that is there any incremental advantage to either have to recalculate the SNM every single time, or can you do that incrementally in some ways?
No, so at the moment we are computing it at every single time. But theoretically, what you could also do is you could save outcomes for certain calculations, looking at the distribution of the belief, right, and then reusing these results in a later time. But at the moment, we evaluate it at every step.
Okay, one last question. I'm going to go for a back row person.
How do you choose a threshold in this case? Is there a way where you can get some guarantees by choosing different values of threshold?
No, so at the moment we don't have any theoretical guarantees. The way we chose this threshold, we ran a set of preliminary tests to figure out the best threshold for the problem scenarios. So at the moment, this is also one of the limitations of this method here, that this threshold has to be user-defined. So we could think of other methods where we actually look at the hardness of the problem and then figure out what is the optimal threshold. That would be another approach in the future, yes.
All right, thank you very much.
Thank you.